Welcome everyone watching on YouTube. So this is our 74th live stream geometry. We have 3 people here with us today so far, and I'm sure more might join later. And I'm taking problems again from the website of Jean-Louis Aimé. So I think he's a retired French professor, and he has some really great problems on it, and he gave me permission to use them. So I'm going to keep doing it today. Some of them are in French, so I had to translate them into English. But I like most of them aren't super heavy on like having to know previous configurations. And a lot of them are like really elegant. So if you want to join us in the future on this session, feel free to email me at mgreenb801@gmail.com. It's going to be in the description of the video, and we meet every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. Can everyone see the first problem? So Jean-Louis Aimé, his website has like a whole bunch of different volumes of stuff. So this is from volume 50. So I'm going to start with this first question. I think we might have done this before, actually. I don't remember how we did it, though. It's been a long time. So let me actually, for BC, let me draw a line instead of a segment. So M is the midpoint of BC. And then we draw the circumcenters of BAM and CAM. And I think this actually has a name, this problem. I think it's called Sparrow's theorem. So I'm going to draw the circumcircles of BAM and CAM. Whoops, didn't want to do that. I will do this. Then I'll draw the centers of those 2 circles. They'll be IB and IC. So we have this. All right. So it looks like we have another person joining us. Okay. So this will be IB. And the other one will be IC. Hi, Prathamesh. Thanks for joining us. So we're on our first problem. And I'm taking them again from the website from Jean-Louis Aimé. So let's draw the circumcircles BAIB and CAIC. And we want to see where they intersect BC. So we call that P and Q. Oh, that's weird. So I thought, like, I didn't think they would intersected at the same point. I thought they, BAM and CAM. So basically it's saying that they pass through the same point. I thought P was on one side and Q was on like a different side. Let me see, is it possible that P and Q are on different sides of the triangle? Like, what if I make this really obtuse? No, I think P and Q have to be on the same side. Like, I think P and Q are the same point, right? I don't think we can do it. It's weird that the problem would be stated like this if P and Q are actually the same point. But so really it's saying prove that P is equal to Q. Okay. So I guess I'll just solve it that way. So basically we want to show, if we call it P, then we want to show that CICAP is cyclic. Can we use the McKell point? Maybe. It does kind of look a little like McHell point, right? Because let's see. Yeah, it looks a lot like it. Let's see, because then we would have this circle and this circle would both pass through that same point. I wonder if P, IB, and IC are collinear. Yeah, maybe we can angle chase. It does look like they're collinear. Yeah. Let's see. Yeah. So I wonder if that has to do with it. So basically that would mean P lies on the, because this is the perpendicular bisector of AM, right? So yeah, they are collinear. I don't know. So let's see. If we draw the midpoint of AM, then we know that this is like the perpendicular bisector of AM. We want to show that P lies on it. And we show that PA is equal to PM. Maybe we could use power of a point somehow. It almost looks like, yeah, I don't want to make it look like these circles are tangent. So yeah, can we do an angle chase? We want to show, we don't know that circle exists yet. We want to show it exists. So I'm going to draw in those segments. And we know that ICA is equal to ICC. So showing that it's cyclic is basically the same as showing that this is an angle bisector, which is the same as showing that PA equals PM. So if we can show that, that's the same as saying that these angles are equal. I wonder if it helps to draw this point. Point Q. So we actually want to show point P equals point Q, which would, so that's basically the same as saying that PAICC is cyclic. If we could show that, that would solve the problem. So we want to show P and Q are the same point, so that QAICC is cyclic. And that's the same as showing that triangle PAM is isosceles. And that doesn't seem like it should be that hard. But yeah, I don't know how to do it just yet. Is it obvious actually that PAM is isosceles? If we define, so I think Ravi has a solution. So we take those two. Okay. All right. So what Ravi is saying is define P. I guess we could define P prime to be this point. So yeah, that's a good way to do it because then it's symmetric. And then we can show that P prime lies on both circles. So we want to show, so I can delete E and F. And I think that might solve the problem. So we want to show PBIBA is cyclic. And I think that might just be an angle chase. And then we show PCICA. Okay, so So yeah, okay, you're saying that follows by spiral similarity. So I'll call this point K, and then I'll just say, yeah, so this problem is a little bit easy. I think the next ones are going to be a little harder, but I like starting off with an easy one. So let IBIC intersect BC at K. And then you're saying it follows by a spiral similarity. Oh, because AIBIC is similar to ABC. I think that's kind of the spiral similarity you're saying, right? So triangle AIBB is similar to AICC. Is that obvious? Yeah, so I'll mention it in just a second. Is it obvious though that those are similar? So we're saying this angle is equal to this angle. Yeah. So that's the same as saying angle AMB. Yeah, because, okay, so, or it's 2AMB. Yeah, so, yeah, I wonder, did we even use that M as the midpoint? I don't think we used that anywhere, did we? I wonder if M can be any point. Whoops, sorry about that. I try to copy what Robbie put. It won't let me copy it. Okay, so you have angle AIBB is equal to twice angle AMB, which is 2 times 180 minus angle AMC, which is, and that's angle AICC. So then those triangles are similar because both are isosceles. And once we know that, so AIBB is similar to triangle AICC. Both are isosceles and share an angle. It's weird because I thought, so yeah, I'm gonna finish writing up the solution, but so that basically implies triangle AIBIC is similar to triangle ABC. Here's where we use the spiral similarity by a spiral similarity at A. So basically, if we know, here's what spiral similarity means. If we know that AIBB is similar to AICC, then it's easy to see from using ratios that triangle AIBIC is similar to ABC. And then from there, that means angle, so that would mean angle AIBK is equal to angle ABK. Because those are both 180 minus angle B. And then, so that means that AIB BK is cyclic. And that means that K is equal to P. And then similarly, K is equal to Q. Oh, sorry. Yeah, I don't think we use that M as the midpoint. So let me go back. So P is equal to Q, and so MQ is equal to MP. And that solves it. I didn't think the problem was like this though. Let me go on Jean-Louis's website and check it out. So, okay, actually, I think this was Highway to Geometry. Actually, I don't think it's here. I think it is, I think it's this. So yeah. Let's see. Was it? Yeah, I think it's this. So yeah, it's in so his picture looks more like this. So in his picture, P and Q are not the same point, which is weird. So we have a triangle ABC, M is the midpoint. IB and IC are the, oh, you know what? I think we might have made IB and IC the circumcenters, whereas in this problem, I think they're the incenters. Interesting. Okay. Yeah. So really, yeah, that's so interesting, isn't it? The problem is true whether they're the circumcenters or the incenters. Okay. So we're going to have to redo this, but that's really interesting that the problem still worked. What are the chances that that would happen, right? So I need to make this, see, it was a problem with how I translated it because it was in French. So we'll say it's the incenters. And let's try the same thing. So exactly. So P and Q should not be different. I mean, they should be different. Yeah. So, oops. And now it will matter that M is the midpoint. So M can't just be any point anymore. All right. I knew something was weird. So we have the encircle, that encircle, and this encircle. Okay, so now I'm going to close this. Oops, sorry. All right, so this is IB, and this is IC. And AIBB, AICC. And then this is P, and this is Q. And we want to show MP is equal to MQ, which is the same as showing, yeah, that M lies on the radical axis of those two circles. Yeah, or we could show PB is equal to CQ. Yeah, so yeah, the circle's so big, I could shrink the diagram just a little bit. So yeah, it's equivalent to showing that the line passes through these circles. So yeah, let's think about that. It's worth drawing the centers of these. So we want to show M has the same power with respect to A, B, IB, and A, C, IC. But we know these are, oh no, these are not collinear, are they? I didn't think they were. Is that true that those are collinear? It's about joining AP and AQ. Wait, why are these collinear? Is that obvious? Is it just an angle chase or something? I don't see why they should be. Because yeah, once we prove that, then I think it's just, I wonder if this is cyclic. Yeah, well, oh, you know what? I don't know if they are actually collinear. I think it might be an illusion. Yeah, this isn't cyclic, and the fact, since it's not cyclic, I don't know if these are actually collinear. Oh, this point right here? Okay. All right, I'm gonna hide one of them because yeah, we don't know yet that they all meet. But I don't even know, let me try something. Let me see if these are really, yeah, it looks like these are collinear, right? I don't think that's a mistake. I think they're collinear, but is that obvious? PFAB must be an isosceles trapezoid. If they are, yeah. So yeah, they have to be collinear. I just don't see why. Or maybe first we could try to show those isosceles and then it would follow from that. So let's do an angle chase. We could try to show circle with diameter BC. Okay, so yeah. Well, basically, I mean, basically, if we draw the circumcircle of ABIB, then we want to show that MB is equal to MF. that seems like it shouldn't even be that hard, right? So really we just, oh, that's obvious because this is an angle bisector, right? So since AIB bisects this angle, then BIB is equal to IBF. And then from there, it's obvious that these triangles are congruent. And so BM equals FM equals MC. And then, yeah, I think the whole problem falls from there, because then MB times MP is MF times MA is MC times M. Well, yeah, like, yeah, from there it's obvious. Okay, so all right, so we can write that out. Yeah, that wasn't that hard either, even with the incenters. All right, so let me make the diagram smaller. Let's see, maybe something like that. And so I'll say, let the circle ABIB intersect AM again at, what was it called? F at F. Okay. So then, since AIB bisects angle BAF, that means that BIB is equal to IBF. And then we also have, so that must mean that MA is equal to MP. Yeah, basically just power of a point now, right? It's pretty simple because MB times MP is equal to MF times MA. So that implies MP equals MA. And then similarly, MQ equals MA, so MP equals MQ. That's too easy. All right, so I will move on to the next one. Yeah, I think they're going to get harder. This one looks tricky. So we have a triangle ABC, and we draw the orthocenter and the 9-point center. I'm going to first draw the altitudes because we're going to use them later. Whoops, let me delete this. What is going on here? So D, E, and F will be the altitudes. And then H is the orthocenter, and then we want to draw the 9-point center. So we can just draw this circle, and then the center of it will be the 9-point center. Call it N. And now we draw the perpendicular bisector of BH. We see, where does it meet EF? and we call it L. And we want to show that LH is perpendicular to AN. So we have a little bit of interesting inference. So this is obviously going to pass through these 2 points. That's a well-known fact about the 9-point circle. And we also have the midpoints here. So these are the midpoints of the 3 sides. Let me hide some stuff. Yeah, maybe this isn't that hard actually. I hope you guys didn't solve it already. I'm going to check the chat in just a second. Let's see. That. Oh, you did this a week ago? Okay, don't spoil it. Let's see if we get the same solution. So okay. Is there another circle we can draw? So what can we say about AN? Basically, I wonder if we can make an orthocenter somehow, because what if we let AN meet this? So we know H is the orthocenter of ABC. Maybe it's also the orthocenter. Like if we let AN meet this, then H should be the orthocenter of that triangle. It almost feels a little like Ricard's theorem. Like, what if we let GF and EI intersect? Or something like that. Yes, don't give us too many hints. But yeah, it does feel like Ricard's theorem. So I haven't used Ricard's theorem in so long, but let me try that. So we let these intersect. Oh, but then that would be saying HN is perpendicular. We want AN. So, but what if we look at MFEK? So, oh, but then it would be where FK, yeah, this is a little tricky. Let's see. I wonder, yeah, let me get rid of those two. So if we look at MFEK, then, oh, but they don't pass through L. Okay. But yeah, but basically we could still try to use Ricard's theorem. So this means that LH, this means that this intersection has to be collinear with A and N. If we can prove that, that would solve it by Ricard's theorem. Yeah, so we want to show that O, let me call it P instead. We want to show that P, A, and N are collinear. That would solve it. So let me hide, let me just draw the segment. Is it just harmonics? Let's see. So yeah, how do we show P, A, and N are collinear? Is there something special about this line? Let's see. No, J's not on the line. If we wonder if there's something special about it. Oops. There's something special about either of these points? I don't think so. BJK. I doubt that's, yeah. Yeah, we could try to show, so we want, maybe we could try to show angle GPN as angle, well, no, that's not gonna work. So I wonder if A is like the orthocenter of PFE. No, it's not. So G is the midpoint of HB and I is the midpoint of HC. Could it be a homothety? So a homothety about H with ratio 2. Like what if we reflect H about A? I don't know if it, collinearities and intersections of lines and circles. Oh, Pascal. Oh, good point. So we want to use Pascal's on MFEKIG, possibly. Let me write this on a paper so I can remember the intersections. So let's see. So we have MFEKIG. KIG. All right, so we found the same thing. So we have F and E. So we want to see where F meets through M and G, and we want to see where E meets through K and I. But wait, how, I'm still trying to think how to use Pascal here. So we have those 6 points, but I'm not sure. So is it because MKIG is a rectangle? So yeah, basically, so MN and I are collinear and GN and K are collinear because basically this is a rectangle because M is the midpoint of AB, G is the midpoint of BH. So we have MI and GK, MF and KE, and GF. Okay, I think I got it here. So MF, so yeah, I think that works. So K, we have KG and KE. So we have the intersection of MF with KE, and then we have MI with KG, and then like is this just Pascals? Like yeah, I'm really bad at applying Pascals, but I guess it just says that PA and N are collinear, right? But shouldn't one of the intersections not have M in it? Like, I guess the way Pascal's works, like, shouldn't one of the three intersections not have point M in it? That's what I thought, right? Or is that okay? Like, because like, I thought in Pascal's it's like M would be in two of the three intersections, but not in the last one. That's why I'm confused. Oh, but it's GF. This is GF intersect EI. So yeah. So wait, MF intersect KE, and then MI intersect KG, KGF. Okay, all right. I'll just put that as a solution. Okay. So yeah, this problem is also a little bit easier once you see that to use Pascal's. So let GF intersect EI at P. And I'll say like let G and I. Yeah, first let me define those points. So let G, I, M, and K be the midpoints of BH, CH, AB, and AC. Then G, I, M, and K lie on the 9-point circle. Oh, there's what's OMC? So I'll have to check it out after the session. So GMKI is a rectangle. Oops. Oh, really? I should check it. I should really check it out then. GMKI is a rectangle. So I'll just say it like this because we have GM is parallel to AB and KI is parallel to AB. So All right. And so GK and IM intersect at N. By Pascal's theorem on KGFMIE, we have P, A, and N are collinear. And then by Bricard's theorem, LN, by Bricard's theorem, LN is perpendicular to N, LH is perpendicular to NP. We have LH is perpendicular to PN, and that means that LH is perpendicular to AN. And I'll add one more step here because GI, so they lie in the 9-point circle, and L lies on GI. That's kind of obvious. So, all right, so I'll move on to the next one. Okay, this one's kind of interesting. So we have a triangle ABC, and H is any point inside of it. So not the orthocenter. But I remember the way the diagram was, so we call this H, and then K is the orthocenter of ABH. So oh, you know what? I gotta switch. Okay, I'm just gonna, for now, I'm gonna do it like this. ABH4, but I'm gonna make A on the bottom and C on the top, like that. So K is yeah, let's make H. We want H to be inside the triangle. But yeah, we can make it something like that. That looks good. So H is the orthocenter of ABK then. So the line going through, so the line going through H perpendicular to BC, we want to see where that intersects AK. And then we want to draw the line through H. Oh, whoops, I want it the line through H perpendicular to BC, and then the line through H perpendicular to AC. And I want to see where it meets AK and BK. So this intersects AK at E. And the other one, let's see if I can get it to intersect the side BK. Is that possible? I think it might be hard to do. Yeah, it might be impossible. Like, yeah, I might have to draw line BC. Like that. So this will be F. And we want to show that CH is perpendicular to EF. All right. So the Olympiad server, do you know if it meets every Sunday at the same time? Just because if it meets at the exact same time as this, I might want to change it to a different time, but I don't know if that's the case. Perpendicular. Oh, I don't think I drew these right, did I? I want to draw, let's see, the perpendicular from H to AC and BC. Like, yeah, I don't think I drew point F right. Let's see. Oh, maybe I did. Yeah, it's just. Oh, no, I didn't. So the perpendicular from H to BC, okay, this should be point, so point E I didn't draw, right? So this should be point E. So H to BC and H to AC. Okay, so let's draw this point right here and this point, and then I can hide everything. And do you know if it's like every Sunday at the same time, or is it just this week? All right. Like, yeah, do you know if it happens every week, or was this like a special week? And it doesn't happen every week. Ah, okay. Yeah, I guess I'll find out from the other people that are on it. All right. So let's see. So K is the orthocenter of ABH. We want to show CH is perpendicular to EF. So basically, almost every week. Okay. All right. I might want to change, like if it's always on Sundays at the same time, then I might want to change the time we do this. I'll think about it more. But yeah. So yeah, we'll see. Okay, so we want to show CH is perpendicular to EF. Something feels weird about this. So F is supposed to lie. Yeah, I didn't draw this right. F is supposed to lie on BK. So I was going to say something that didn't feel symmetric about this. So yeah, it's not where it intersects BC, it's where it intersects BK. So I'm going to delete EF and I'm going to delete point F. And I'm going to draw, whoops, sorry. I'm going to draw the whole line BK. And this is F. There we go. I think I finally got it right. All right. There we go. I will shrink it just a little bit. If I move point H down, that'll move K up a little bit. I think that's a good picture. It almost looks like GB is parallel to AB, but I don't, is that true? Maybe that's obvious because Yeah, I think it might be obvious because angle HGB is angle HCA. And HCA. Oh, maybe it's not true. Let me use the parallel line. Yeah, it's not true. All right. This is a tricky configuration. Let me draw in the perpendiculars from A and B and C. That might make it just a little bit easier to understand. So So if CH is perpendicular to EF, I wonder if H is the orthocenter of CEF. Let's see, is that true? Yeah, there's a lot of right angles. Okay, H isn't the orthocenter of CEF. But yeah, there's a lot of right angles here. So we have a couple cyclic quads, right? This is going to be cyclic. And this is going to be cyclic. So we have all 5 points. That probably helps, I would think. Can we use the radical axis theorem somehow? So like, yeah, and I guess it's kind of obvious that this is cyclic, right? And this is cyclic. So we have a lot of circles. So CH, I'm going to hide those circles because I feel like it might make it confusing. We can calculate the angle that CH makes with DG. Can we find the angle DG makes with EF? Let me draw EF. I'm going to draw the whole line. Let's see. Is DG parallel? No. 1 sec, guys. I'll be right back. All right, I'm back. So yeah, I'll draw EF. Thanks for waiting. Oops. Maybe we could show EH squared, HE squared minus HF squared is CE squared minus CF squared. I don't know how easy that would be. Maybe we could drop a perpendicular from H to EF and then try to use the radical axis theorem. That's something I've done a few times before. So if I draw the perpendicular from H to EF, basically I want to show that it passes through C. Is there a way I can use the radical axis theorem? So we know that HJEM is cyclic. And we know that HG, you know that HL FM is cyclic. Is there some other circle that we can use? So we have HM and these two circles. Maybe we could try to see where BC meets that circle. Let me try something different. Like, I wonder if we let BC intersect that circle in 2 points, I wonder if there's something special about those points. So there's this point, and then there's this point. Is there anything special about these? I doubt that this actually concurs. CA intersect BK. Oh, it looks like NH intersects on this circle. So we'll have to think about that in a little bit. First, let me read what you just said. So So yeah, CA intersect BK is the orthocenter of AHF. And then this same, okay, so AHF. So PH is perpendicular to AF, is what you're saying. And because FH, oh yeah, because FH is perpendicular to AC. Yeah. So PH is perpendicular to AF. And then we could find another point that's perpendicular to BE. Okay. So let me think about what was it that I saw. So I said NH. It looks like NH and AC meet on that circle. Let me try OH. And so this is really interesting. If you draw the intersections of NH and OH with AC, they meet on this circle right here. That's kind of interesting. I wonder if that's equivalent to the problem itself. Okay, if the problem is true, then that would be true. Yeah, I feel like maybe it's making things more complicated by adding these points. Like point M wasn't there in the beginning, so I don't know if this is really making things easier. Yeah, let me delete this point M. I feel like it's making things harder. So maybe I should draw the intersection of BC and AK because I drew P. Now maybe I should draw the other one. So like this point. I wonder if PQ is perpendicular to AB. So if I call that point Q, is PQ perpendicular to AB? Let's see. So C is the orthocenter of BHE. I'm sorry, Q is the orthocenter of BHE. So we can find the angle that PH makes with AF, and then the angle that QH makes with BE is 90. So basically, angle PHQ is the angle between BE and AF. This is tricky. I want to use that angle BGE is 90, not just BGH. Is there a way? Because there's some other right angle. So angle BGE is 90. So we have more like, yeah, like we have another cyclic quadrilateral here, right? BGJE. And then we have AFDL. And I don't think those actually both pass through, only one of them passes through G, but yeah, we have a lot of cyclic quadrilaterals here because this is cyclic. And then, yeah, and then this one is also cyclic. And then this is cyclic. This is making my head hurt. So two of them pass through BG. And then two of them pass through AJ, but a different two. And then these pass through HI. I'm not even sure. Yeah, like what if I try to use the radical axis on this, and the one passing through BG? So that would mean BGIH. Then I would have to draw this point right here. So we're saying BGIH and JM concur. That's a lot of lines. So BGIH and JM concur. And yeah, it's getting kind of messy, but I think we also need to draw this point right here. So BC, so we have BC, IH, and AJ. And then we have AC, IH, and what's the other one? I think it's ACIH. So we have BCIH. So let's go through some special point. BCIH and JA. And we should have ACIH and some other point. I just can't figure out what that other point is. So I use the radical axis theorem on these three circles. Now I want to use it on these two and this circle, I think. So I'd have AC, okay, these two intersect at AC, these two are at IH. Oh, because there's like a little tiny, teeny tiny point here that I can't see. It almost looks like those are tangent at L, but they're not actually tangent. So yeah, this is getting a little confusing, but if I draw that point NL, basically NL passes through this point. That's what I was thinking, which lies on IH. But yeah, I don't know if any of this is actually helpful. Yeah, I don't think this is going to be too helpful. So I'm going to erase some of the stuff. Oh, this is hard. Just so many right angles. Um, let's see. CH is perpendicular to EF. That's what we want to show. How else would we do it? Are there any like similar triangles? What about, okay, I think I have an idea. If I, so what if I let DA intersect EF and, or if I let AC and AB intersect EF? I'm going to delete P and Q. I just feel like, and I'm going to delete these circles. Actually, you know what? I'll leave this one. I want to use that angle BGE is 90. So BGE is BJE. So yeah, if we have these two circles right here, can I use the radical axis theorem somehow? But I don't want to have to create this point. So if I draw the circumcircle of JEH, you know what? What if I did this? I draw the circumcircle of HJE. So basically it's like the point M that we had before. Yeah, what if I use the radical axis theorem on these three circles? So this is the perpendicular from H to EF. And okay, so BG is one of the radical, BG, JE, oh, but then I get the point Q again. And then I'm just saying that Q lies on the radical axis of these two. Let me try a different circle. Actually, I kind of like this because it uses all the different right angles. So like, what if I brought back this point? Oops. Basically, I'm saying N lies on the radical axis of those two, right? So I wonder if B, O, and E are collinear. Oh yeah, they have to be, because this is 90 and that's 90. So H is the N is the orthocenter of HBE. That's kind of basically what you were saying before. So we have a lot of orthocenters here. Is GHDEF cyclic? I don't think GDEF, yeah, GDEF looks cyclic. Did we already know that? Because angle F, maybe yeah, because angle FDE, actually, I don't think that's obvious. GDEF. That would prove the problem. How would that solve it? Oh, because that would mean GD is anti-parallel to EF. Yes. I like that idea. I'm going to delete. So but angle FDE is angle HDE, and angle FGE. Yeah, I think that's the way to go. I wonder if GBF is similar to GDE. Well, that would be the same as saying that angle GBL is equal to 180 minus GDE. Which is GFE. Is GBL equal GFE? I don't think so. No. Yeah, I think we're close. I'll be right back. All right. GDEF. And we show GH. Yeah, that looks like it might be a good way to do it. So GH times HE. And we know that BGHO is cyclic. So that's the same as EO times EB. Well, no. That would be, sorry. So GH times HE is BH times HJ, right? Oh, and I think that solves it because GH times HE is BH times HJ, which is AH times HL. And that is, oh, because I hid the other cyclic quadrilateral. AH times HL. Wait a sec. So BGJE is cyclic, and what's the other one that's cyclic? BGJE and I'm just getting so confused here. So it would be AF, AFDL is cyclic, right? Because ADF is ALF is 90. And so HD, yeah, okay. So that solves it. All right, so I'm gonna type it up. And we can delete 0.0. And do we need these circles right here? I don't think so. Let's see, GH times HE. I don't think we need these. So yeah, basically we're using these circles. Wait a sec. BLJA. That's the last circle. Yeah, okay. So okay, so yeah, this shouldn't have been that hard, but yeah, it was just confusing with all the right angles. So so angle ALF. So first I'll define I, J, and L. So let I, J, and L be the feet of the altitudes in triangle KBA. And then angle ALF equals angle ADF, which is 90. So that means that ADLF is cyclic. And then similarly, BG, what is it? BGJE is cyclic. Did we define G? So E and F, G. Yeah, there's no G or L. Well, we define L, but there's no D. Yeah, let G and D be the altitudes. Yeah. D be the feet of the altitudes from H to, let me check the chat. Yeah, exactly. From H to BC and AC. And then we have angle BLA is BJA is 90. So this is like, you know, trivial, but I'm just going to write it anyways. This is always true in any triangle. Cyclic. But yeah, there's 4 different circles here. So did I miss one? BGG. So this BGJE. Oh, the one that we're trying to show is the one that I missed. Yeah, so, okay. So now I'm going to write out what you wrote. And then we have so obviously CGHD is cyclic. So yeah, I wonder if there's like an so I think he's a retired math professor from France, I'm pretty sure. So I think when he was working, he used to just do geometry, I think. Now he's retired. But that's my understanding. I'm not 100% sure though. All right, so so CGHD is cyclic and GD EF is cyclic. Combining those two, we get CD is perpendicular to EF. So, well, yeah, what's a better way to write that? Because like, so the angle that CH makes with EF is the angle that CH makes with GD plus the angle that GD makes with EF. And then combining those two, that's kind of how you get it. But so yeah, like I'm trying to remember the proof of this. Like I know that GD is like anti-parallel to EF. And then I know that CGHD is cyclic, but how does that, is there like an easy way to see that? You just say, yeah, I'm trying to think. HC passes through the circumcenter of GHD. So it's an altitude. Okay. That's a good way to put it. Okay, so I like it. Oops, sorry, I didn't copy right. Copy. I don't know why it won't copy. I'm just going to type it up. HC passes through the circumcenter of GHD. So it is an altitude in HFE. All right. So I'll say HGCD is cyclic. With diameter CH. All right. So since GHD is similar to HEF. All right. So, and then that means that CH is perpendicular to EF. All right, so I'm going to move on to the next one. That was a good idea to, yeah, try to prove this is cyclic. Okay, so we have almost an hour and 20 minutes left. Okay, so we have a triangle ABC with D is the midpoint of BC.